Greetings and welcome to this sixth video in the introduction to R series. In this video we will be going through some of the basic data analysis functions provided by R. So far we have primarily been going through creating and manipulating data structures, and we have also been going through how to use or download and use user-written packages. And now we will be going through some of the basic functions provided by R, relying on some user-written packages, but not many, to complement the existing functionalities of R. Now, the types of analysis that we'll be going through is the covariance and correlation analysis, which is provided by the cov function for covariance and the cor function for correlation. We will also be going through how to do bi- and multivariate regression, that is linear models, using the LM function, which stands for linear model. And we will be looking briefly at the generalized linear models, which allows you to do logistic regression for one, which is what we will be looking at in particular. So this can be done using the GLM function provided by R. So this is not an exhaustive list of the types of functions and the types of analysis that you can do with base R. Some other notable mentions, which are quite commonly used within the fields of psychology and education, where I stem from, are the t-tests, which can be done using the t-test function that allows you to do all the types of t-tests. And you have the chi-square test, which allows you to do, obviously, chi-square tests. So the packages that we will be looking at in particular as part of this video is the psyc package, which provides some additional functionalities, or provides a lot of additional functionalities, but in particular we will be looking at what it provides for making correlation analysis a bit easier. And as for the linear models, we will be looking at using the lm.beta package, which allows you to get standardized regression coefficients, something that R does not provide you an easy option of getting using the LM function. So before we start with going through these functions, let us first get some data to play with. So let's use the mtcars dataset, which R comes with. You can get this using, by the way, if you use data in parentheses, you can go through a number of different datasets that R comes with by default. But in this case, let's just do mtcars. So opening this, printing it to the console, we see here that we have now got this mtcars dataset loaded. Now I want to make a couple of adjustments to it for the purposes of demonstration later. Let's add a new column to it, mtcars cbind row names. Call this names, row names, mtcars. You'll see we added the names of the cars as a variable here, and we change the row names of mtcars now to run through and row mtcars. And now we removed the names as row names and replace them with simple numbering. Now, what these different variables represent, you can actually open up a help file which comes with R, where you can see here you get an overview over the different variables that are contained in this dataset. See, there are miles per gallon is the first column, now the second column since we added the car names as a new variable there. The number of cylinders, displacement, horsepower, axle ratio, etc. So that you can have some intuitive understanding of what these different variables represent when we now proceed with doing some analysis. So now we have a data set to play with, and we can start off with doing correlation and covariance analysis. So starting off with covariance. The covariance can be between two or more variables, can be obtained using the cov function, which comes with base R, where the first argument is either a matrix or a data frame consisting of the variables, or a single variable, and if you specify only a single variable, then you have to specify as the other argument the variable that you want to covary with the first variable, the second variable. So what we do here, if you want to covary or find the covariance between, let's say, the number of cylinders and the horsepowers of the car, we can do this. So this here is a data frame, so we can do MT cars and use this dollar sign here, so we can conveniently cycle through the different variables. So here we take the empty cars sil and the empty cars horsepower, and we get the covariance, which is 1 or 1.93, etc. So this is not necessarily intuitively meaningful. An more intuitive quantity is perhaps the correlation coefficient between the two, and the correlation you can get through this. And we see that a correlation, or the Pearson correlation coefficient between the number of cylinders and the horsepowers of the car is 0.832, etc. And you can get then the R squared by squaring this output like this. You see that the variation in one of these variables explains approximately 70% of the variance in the other variable. So as previously alluded to, you do not necessarily have to do this two or one variable pair at a time. You can actually input several variables at once, and you can then retrieve a covariance or a correlation matrix. So in order to get the covariance or correlation matrix from all of the variables included in this empty cars, you can do cov and simply provide the dataset as the input. However, this requires that all of the variables that are included in the dataset can be subjected to numerical manipulation or arithmetic operations. And since the class of the first variable is character, that means that this function will crash if you try to calculate the covariance between a character vector and a numeric vector. So we have to subset this data so that we don't include this the first variable. So we can do this simply by using these brackets here and saying empty cars minus the first. So we ask for the covariance for the empty cars dataset minus the first column. And here we get the covariance matrix for exactly this. So we can do the same for correlation. Let's do correlation. And we get the correlation matrix for all of the variables contained in this data set, except for the first one, because that was a character vector, which means that you cannot calculate the covariance or the correlation of a string with numbers. So you do not have to supply all of the variables in the data set. You can be selective and say that we want to just have the correlation between, well, we can first of all try just two empty cars, and we take the SIL and the HP horsepower here, and we get this small correlation matrix here, which is just these two variables. And we can add, let's say, we can have the WT, the weight variable, and we get this 3x3 correlation matrix. And you can keep adding the variables that you want to this in this manner, so that you do not have to print out the correlation matrix for the entire data set all the time. In order to significance test these correlations, R comes with a function called core test, where we can take, for example, the MT cars cylinder with the MT cars horsepower here, and we get this significance testing here, where we have the T value, the degrees of freedom, and the P value, which we see here, is very low. So that means that this correlation that we observe here is quite significant. And here we also get the 95% confidence interval around this correlation estimate. Unlike the core function, the core test function does not allow for calculating or for significance testing all of the variables in the dataset at once. It requires that you only input the two variables at a time, so you can only significance test two variables at a time. However, the psyc package comes with the functionality of significance testing all of these variables at the same time. So when I load psyc here, you can see that there is one naming conflict with another package that I have loaded, but that's not important for now. We're not going to use the AUC functions. We can use the core test function from psyc, as you can see here. And we can supply the MT cars dataset as above. And what we see here then is that first we get this correlation matrix, and here we get the probability or the p-values associated with each different pairing of variables. So we see here that there is a correlation that has a p-value of 0.62, which then corresponds to this value here. It's the DRAT value, DRAT with carb. So DRAT with carb, we see here that this correlation is minus 0.09, which is very small, which makes then this very high p-value fairly reasonable at first sight. So the core test function provided by the psyc package then makes life easier for you if you want to be significance testing the correlation between several variables at once. So that does it for correlation and covariance analysis in R. We'll be going through the core and cov functions as well as some other support functions. So now we will be going on or moving on to the LM function, which is used to fit linear models. Now, covariance and correlation analysis make up two types, very strongly related types of linear models, but the LM function allows you to extend this type of analysis to the multivariate case, that is more than two variables. So if we first then pull up the help menu for the LM function, we can see here that, as I just said, the LM function is used to fit linear models. So linear model is basically a regression. However, it's also used for analysis of covariance or ANOVA, or ANCOVA or whatever. So regression analysis and ANOVA analysis basically amounts to the same thing. They're both linear models, so they can be done interchangeably. However, there is slight differences in output when it comes to the AOV function as opposed to the LM function, which we will be going through now. So as we can see under usage here, the LM function includes the formula as the first argument, and second, optional actually, is the data that the linear model is to be fit to. It's optional in the sense that if your data is not stored or organized in a separate data structure, such as a data frame, which MT-cars is, but the variables that you want to include in the linear model is stored or are stored in the global environment separately, then you do not have to specify a data structure that R is to enter and retrieve the variables from. And as you can see here, there are a number of different additional arguments. However, for our purposes, we will be restricting our focus to these first two here for now. So the formula specification for the linear models, or the LM function, goes something like this. You have the outcome variable, tilde input variable. So outcome variable, tilde input variable, or dependent variable, tilde indep variable. That is, the dependent variable is to be explained by, this tilde can be read as is to be explained by independent variable. So using the examples above, we can ask for the LM function to fit the following model to the following variables. We have the let's see, the horsepower variable, and the is to be explained by the MT-cars SIL variable. So if we run this, we get the intercept and the unstandardized regression coefficient. So basically, as the number of cylinders increase by 1, the average increase in horsepower is 31.96. Now you can see here in my model specification here, I specified the data structure that the variables were to be found within the model specification itself. However, I can omit this and add as the data argument that R is to find these variables within the MT-cars data structure, the data set that I have up here. And you get the same thing. If I do not specify where R are to find these variables here, R will look for these variables in my global environment and not in any data structure that is located in my global environment. And since I do not have since I do not have a vector called HP or a vector called sil in my global environment, R will not know where to find these. So I can retrieve from empty cars. Let's say that I want the HP, empty cars HP, and sil. If I now these values can be found in my global environment, and if I then run this code again, now since I did not specify where R should find these, it looked for them in my global environment, and since I had them here, it fit the model. So extending this model to include additional independent variables is quite simple. We can add additional variables, that is to explain the dependent variable, by simply specifying more following the plus sign. So if we check out the empty cars dataset again in the help file, we can see here that this VS variable here codes whether the engine is V-shaped or straight. So this is coded as 0 for V-shaped and 1 for straight. If we can add the VS variable, and we specify again the data here, the object where R is to find these variables. So if we do this and run it, we get the following output. We'll see here that first of all the intercept changed when cylinder and V-shape are both at 0. The horsepower is at minus 15.63, which is kind of nonsensical. However, with including this V-shape variable here, we see that as controlling for the number of cylinders in the engine, when the engine goes from V-shaped to straight, the number of horsepowers decreases on average by 19.11 points. And extending the model further to include even more variables, can simply keep adding more variables using this plus here, and that does now take the let's say AM for whether it's got the transmission is automatic or manual. So again, this is a dichotomous variable going from 0 to 1. Running this. We see that as the transmission goes from automatic to manual, controlling for the shape of the engine and the number of cylinders, the horsepower increases by roughly 40 for every unit increase. That is, as you go from automatic to a manual transmission, according to this analysis. So this output here is kind of Spartan. That is, it doesn't tell you that much. The object that is produced by this function call here is an LM object, a model object. So we can store this then as my model. We see class my model. We see that it's class LM. So we can feed this object then to the summary function, which provides much more detailed information about the model. So the summary output then, when you feed the summary function, the my model object, you get here then some diagnostics for the residuals. the minimum residual, the max residual, and the first quantile, the third quantile, and the median. We get here then organized the regression coefficients. So here you have the intercept, you get the standard errors, which you didn't get before, you get the t-values, and you get the significance values. So what we can see here then is that whether the engine is V-shaped or straight is highly insignificant, so to speak, while whether the transmission is automatic or manual is, let's say, barely significant. It's below the value of 0.05, of here a bit lower, so that's fine. And you see if you have the significance test for the intercept, whether the intercept is significantly different from 0, which it is not according to this, and the most definitely the strongest predictor of whether or of the horsepowers of the car is the number of cylinders that the engine has. So furthermore down here we get some additional values here. The residual standard error, 36.43. You get the multiple r squared, which is 0.7451, which means that these independent variables here together explain roughly 75% of the variance in horsepower. You get the adjusted r squared, which penalizes for model complexity. Otherwise it's kind of hard to interpret, but it seems that adding, well in this case adding the VS and the AM variables causes some penalty because they don't contribute meaningfully to the model. You get the F statistic, you get the degrees of freedom, and the overall p-value for the model, which is highly significant in this case. So going even further, you can get the ANOVA table for this model by feeding the myModel object to the ANOVA function. So going here then, you get the analysis of variance table, the f-test basically, where you get the sum of squares, mean squares, you see the degrees of freedom, etc., the f values and the p values associated with each of these f values given the degrees of freedom. So this is basically all the output you need for a regression analysis that is found by fitting the model and subjecting the model object that you make using the LM function to the summary and the ANOVA functions. So a neat thing about the LM function is that it does not necessarily need to be fed numeric variables. So let's see, we have the empty cars and we go to the gear variable. So we see this here is numeric, it's integers ranging between 3 and 5. Let's check the class of this. So that's numeric. However, for the purposes of demonstration, let's turn this then into a factor variable. Now it's a factor. Let's print it and see what it is. So we have 3 levels here. That's the number of forward gears, as we see here. So the LM function actually handles factor variables. It treats them, or it breaks it up into different dummy variables. So if we add this variable then, gear, to our model and run it, we see here now that this gear variable is represented twice in the summary output. This is because gear 3 is then the reference category, and the one variable gear has then been broken up into 3 different variables, or 3 dummy variables, gear 3, gear 4, and gear 5 automatically by the lm function. So storing, if you want to dummy code variables, you do not have to dummy code them manually if you want to use it, or use a dummy variable in an lm function call. It's enough to simply store the variable as a factor type data structure and include it in the lm function call, and R will handle the dummy coding automatically for you. So now let's move on to interaction analysis. So the lm function makes specifying interaction terms, and as with the dummy variables, actually makes it very simple to produce interaction terms for your model. So to add an interaction term between 2 variables, let's say that we want to get the interaction between, well, it's kind of nonsensical, but let's take the interaction between V-shape and automatic or manual transmission. So then we simply add a new variable here. We say vs comma, or sorry, colon am. Run this, and we have added the interaction term vs am, which we see is non-significant. But anyway, here is a very simple way of adding an interaction term to your model without having to make a new product variable. So another way of doing this is to simply add this multiplier, the star, in between the vs and the am in the formula specification. And you see here that the output is exactly the same. So what this star here then does is that it tells the lm function that in addition to the main effect between vs and am, as was specified with the plus sign here, you want to include the interaction term. So if you want the interaction effect in addition to the main effect. So if we do this instead, we do not include the main effects in the model. For that, you need to specify the star or plus, in which case, if you just have the plus here, you do not include the interaction term. If you do the star, you have the main effect in addition to the interaction effect. And if you have the colon, then you have the you have only the interaction effect included in the model. So in other words, if we have only the cylinder here and the V-shape variables, writing this plus cyl colon V-shape is equivalent to writing cylinder multiply V-shape. And if you do only this, only use the colon here, then it becomes a bivariate regression analysis with only the interaction term cylinder and V-shape as the predictor. So one thing that the lm function does not offer, and that you might want, is the standardized regression coefficients. So for this, you can use the LM beta package. So if we do library.beta, the lm.beta package provides the LM beta function, which takes as the argument the object, the model object, which we have here, my model. Now first let's simplify this a bit and make it a multivariate regression. So like this. So now if we feed the my model, we can first summarize this, and we see that we get the standard output. If we then do LM beta and feed it to my model LM object, we get out the standardized coefficient. So the intercept is standardized at 0, and the CIL is standardized at 0.718, and the V-shape at minus 0.14. So this can then be interpreted as when the cylinder variable increases by 1 standard deviation, then the horsepower variable increases on average by 7.718, etc. standard deviations, controlling for the shape of the engine. So this LM beta here produces an object again, so we can call this my model 2, and this we can, as with the output from the LM function, feed to the summary function. And we get output that looks similar to what we would get if we used the summary function on the LM object. It's just that now we also have this column here of standardized estimates. So these standardized estimates here can then be interpreted as correlation coefficients in the bivariate case. So if we then simplify this model a bit more and go back to the bivariate regression model that we used previously, so horsepower is explained by the number of cylinders. If we then use this, get the standardized coefficients, we get a standardized regression coefficient of 0.83, etc. Now if we correlate these two variables, MT cars horsepower and MT cars CIL, we see that the correlation is equal to the standardized regression coefficient in the bivariate case. So to finish off the exposition of the LM function and regression analysis, we go through confidence intervals, which might be something that you want for your regression coefficients. So in order to get the confidence intervals around your unstandardized regression coefficients, which you get from the LM function, you can use the confint function, which comes with base R. So this then takes the model object as input, so the LM model object. So we can feed this function the my model object, and we get the confidence intervals surrounding the unstandardized regression coefficients. So in this case, the confidence interval surrounding the intercept and the confidence interval surrounding the cylinder regression coefficient. So in this case, we see that this intercept here, the confidence intervals comes close to crossing 0, and we see here that this intercept is only barely significantly different from 0 in this case. And this regression coefficient between cylinder and horsepower does not appear to come close to 0. And we can see that this is reflected in the p-value, which is very small. So this is highly significant. So unfortunately, you cannot get the confidence intervals around the standardized regression coefficients that you will get through using the Ln beta function. However, you can standardize the input into the regression analysis to get the standardized regression coefficients. So if we make a new object here, my model 3, and we do Lm, and once again we have horsepowers explained by the number of cylinders, and the data is MT cars. In order, we can standardize the variables by wrapping scale around each of these variables here, which the default setting of scale is to transform the input variables so that they have a mean of 0 and a standard deviation of 1, which is to say that they have been standardized. So if you run this, summary model 3, my model 3, we see that we get out the standardized regression coefficient here, and it's weird like this because the intercept or the intercept is supposed to be 0, but it's not exactly 0. It's an extremely small number here, so we can just for the sake of simplicity remove the intercept by including a -1 here, and we see then that the intercept has been removed, and you have here then the standardized regression coefficient as the estimate. So you can see that it's the same as the one that we got using the Ln beta function above, 0.8324, 0.8324, etc. So once we have got the standardized coefficient this way, that is, we got it through the Ln function by standardizing the input variables, we can then get the confidence intervals around this estimate by using the conf_int function once again and simply supplying the model object, and we get the confidence intervals surrounding the standardized regression coefficients. So in this case here, you see that the 95% confidence interval stretches between 0.625, etc., to 1.039, etc. And you see that the confidence interval in this case actually spans across the theoretically permissible limit, so correlation coefficients cannot be greater than 1, for example, but the confidence interval in this case suggests that the true correlation coefficient can be above 1, which is nonsensical. So this then is a demonstration of how assuming a normal distribution of sampling errors are not always appropriate, and this is especially the case for bounded values such as correlations, which stretch from -1 to +1 and cannot be greater than 1 or lower than -1. So that does it, I think, for a cursory introduction to linear regression. So now we'll be moving on to generalized linear models, which are implemented in R using the GLM function. In particular, we will be looking at the logistic regression functionality of the GLM function, which allows you to predict categorical or binary outcomes from either binary or continuous predictor variables. Fortunately, the GLM function works in quite similar ways to the LM function. That is, it takes as its first argument the formula, so the formula specification, which is incidentally works exactly the same way as it does for the LM function. And furthermore, you have to specify the family, the link function, that is to link the nonlinear link function, that is to link the dependent variable with the independent variables. And following this specification of the link function, you specify the data in the same way that the LM function did, and you have a number of different additional arguments that you could specify, but they are optional and we will not be going into them. So in order to do logistic regression, you need a binary outcome variable. So if we check the empty cars dataset again, we see here that there are at least two binary outcomes. You have the V-shape or the automatic or manual transmission. So these are then good candidates for dependent variables for the purposes of demonstration. So one sensible predictor variable that can predict whether or not the engine is V-shaped, I would say, let's go for the V-shape as a dependent variable. So one sensible variable that we can perhaps use to predict whether a car has a V-shaped engine or not is the miles per gallon variable. So we can specify this within our model up here. We have V-shape is to be explained by MPG, and we specify that the family is binomial and that the link is equal to logit. That is the logistic link function. You can see here that this is the default, so it's strictly speaking not necessary to specify. And that the data is empty cars. And we run this, and this is the output we get. Now, just as with the LM function, this function object that's created by the function, we can specify this as my model 4, can be fed to the summary function to get more detailed output. So this output here can be interpreted as follows. So these coefficient estimates represent, in this case for the intercept, the natural logarithm of the odds for an engine being straight rather than V-shaped when miles per gallon is 0. That is the worst possible car imaginable. And the coefficient for the MPG, the miles per gallon, shows the increases in the log of the odds for every unit increase in miles per gallon. So just as with the linear models, you can also get the confidence intervals for these estimates with the conf_int function, feeding it in my model object. And you get the confidence intervals, the 95% confidence intervals surrounding these parameter estimates. And furthermore, just as with the LM model, you can add independent variables the same way to your model, so you can make this a multivariate logistic regression. We can add horsepowers here as a variable that can help predict whether or not the engine of a car is V-shaped or straight, like this. The summary out. And just as then with the linear models, you can add interaction terms as such by having this star here, and you get the interaction term as well. Now this is a small data set, and this is probably far too few number of observations in order to have a model this complex, but this does it then for the purposes of demonstration.